Today we're going to talk about the matrix math behind transformer neural networks, and we're going to go through it one step at a time. This StatQuest is brought to you by the letters A, B, and C. A always, B, C curious. Always be curious. Note, this StatQuest assumes that you already understand the basics of how a transformer neural network works, and that you are already familiar with the essential matrix algebra that is used with neural networks. If not, check out the quests. In this StatQuest, we're going to learn how the math associated with an encoder-decoder transformer can be written in matrix notation.
Hey Josh, why would we want to learn this matrix notation?
Because understanding the matrix notation will make it infinitely easier to understand how to code transformers and neural networks in general.
Bam!
Specifically, we're going to walk through the matrix arithmetic used by a transformer neural network that can translate a simple English sentence,
"Let's go,"
into Spanish.
Vamos!
Note, we're specifically going through an encoder-decoder transformer and not an encoder-only or decoder-only transformer because encoder-decoder transformers cover everything we'll need for any type of transformer. So, the first thing we need to do is convert the input phrase, "let's go," into word embeddings. Actually, in this example, we're going to start our input phrase with the SOS, or start of sequence, token. So that means we need to determine the word embedding values for SOS, let's, and go. For all three tokens, we use the exact same word embedding network that looks like this, where each input has two separate connections to each activation function, and each connection has a weight, a value we multiply the input by, and then we add those products up before using the sums as inputs to the activation functions. In matrix notation, the word embedding network starts with a matrix that corresponds to the input values, multiplied by a matrix that contains the weights associated with each input. The first row in this matrix corresponds to the weights associated with the input for the SOS token. The second row corresponds to the two weights associated with let's. The third row is for to, and the last row is for go. So, when the input tokens are SOS, let's, and go, then the first row in the input matrix has a 1 for SOS and zeros for everything else. The second row has a 1 for let's and zeros for everything else, and the third row has a 1 for go and zeros for everything else. Now we just do the matrix multiplication row by column.
Beep, boop, boop, boop.
And we end up with the word embeddings for the input tokens. Bam! Now let's move the word embeddings for SOS, let's, and go over to the left and add the position encoding. For the SOS token, which is the first token in the input, we add the corresponding y-axis coordinates from the sine and cosine curves. Then we add the corresponding y-axis coordinates for the second token, let's, and then we add the corresponding y-axis coordinates for the third token, go. Note, in practice, these y-axis coordinates are pre-computed and stored in a lookup table, so figuring out what values to add doesn't take any time. Also note, we'll talk about how the sine and cosine curves are calculated in a follow-up video on how to code transformers. Anyway, now we just do the element-by-element addition to get the word embeddings plus positional encodings for each token. Now we have encoded values for the input tokens, and that means we now need to calculate self-attention. Specifically, that means we need to calculate the queries, keys, and values, using the encoded values for each of the input tokens. For example, to calculate the query values for the SOS token, we multiply the first encoded value, 1.16, by 2.22, and we multiply the second encoded value, 0.23, by 0.17, before adding those two products together. Using matrix notation, we can accomplish the same thing by multiplying the row of encoded values for the SOS token by a column that contains the query weights. Likewise, calculating the second query value for the SOS token corresponds to this equation, which corresponds to multiplying the encoded values by a second column containing 0.41 and negative 0.51. In other words, we can calculate the query values for the SOS token by multiplying them by a matrix of query weights. And when we do the math, we get 2.61 and 0.36. Likewise, we can calculate the query values for all of the tokens by multiplying them by the matrix of query weights. Bam! Now we've calculated all of the query values for the input tokens. Note, before we move on, I want to point out that I labeled the query weights matrix with the transpose symbol. This is because PyTorch prints out the weights in a way that requires them to be transposed before we can get the math to work out correctly. Small bam. Anyway, we can use the same type of matrix multiplication to calculate the key values for each token and the values. Now that we have the query, key, and values for each token, we can use them to calculate attention. We'll start by multiplying the query matrix Q by the transpose of the key matrix K.
Josh, why do we need to transpose K when we do this multiplication?
Well, in this specific case, the obvious thing is that the multiplication wouldn't work. If we didn't transpose K, then the two numbers in the first row of Q could multiply the top two numbers in the first column in K, but then the bottom number would be left out of the fun. So, in this case, multiplying by K without transposing it is a bad idea for technical reasons. However, there's actually a much more important reason to transpose K, and to understand it, let's go through the multiplication one step at a time. We start with the first row in Q, the query for the SOS token, and the first column in the transpose of K, the key for the SOS token. The matrix multiplication gives us the sum of these products, which is negative 4.49. This process of multiplying pairs of corresponding numbers together and adding them up, like we did here, is called calculating a dot product. So, negative 4.49 is the dot product of the query and the key for the SOS token. Dot products can be used as an unscaled measure of similarity between two things, and this metric is closely related to something called the cosine similarity. The big difference is that the cosine similarity scales the dot product to be between negative 1 and 1. In contrast, the dot product similarity isn't scaled. So that makes negative 4.49 an unscaled similarity between the query and the key for the SOS token. Likewise, the unscaled dot product similarity between the query for SOS and the key for LETS is 2.05. And the unscaled dot product similarity between the query for SOS and the key for Go is negative 27.4. Likewise, we calculate the unscaled dot product similarities between the query for LETS and all of the keys, and the unscaled dot product similarities between the query for Go and all of the keys. Thus, by multiplying Q by the transpose of K, we end up with the unscaled dot product similarities between all possible combinations of queries and keys for each token. Bam! Now, the next thing we do is scale the dot product similarities by the square root of d sub k. d sub k is the dimension of the key matrix. And, in this case, dimension refers to the number of values we have for each token, which is 2. So we scale each dot product similarity by the square root of 2. And that gives us a matrix of scaled dot product similarities. Note, scaling by just the square root of the number of values per token doesn't scale the dot product similarities in any kind of systematic way. As a result, our scaled dot product similarities still have a really wide range of values between 5.01 and negative 66.2. That said, even with this limited scaling, the original authors of the transformer said it improved performance. Small bam. The next thing we do is take the softmax of each row in the matrix of scaled dot product similarities. And taking the softmax of each row gives us these new rows. Note, the softmax function makes it so that the sum of each row is 1. So we can think of these values as a summary of the relationships among the tokens. For example, the SOS token is 1% similar to itself, and 99% similar to Let's, and 0% similar to Go. Now let's put these new rows back together to form a matrix. The last thing we need to do to calculate attention is multiply the percentages by the values in matrix V. To understand exactly why we do this multiplication, let's go through it step by step. When we multiply the first row of percentages by the first column in V, we calculate 1% of the first value for the SOS token, and add to it 99% of the first value for Let's, and then add 0% of the first value for Go. And that gives us 1.54, the first attention score for the SOS token. Likewise, we scale the second column of values to get the second attention score for the SOS token. Then we scale the values by the percentages for Let's to get the attention scores for Let's. Lastly, we scale the values by the percentages for Go to get the attention scores for Go. And, at long last, we have calculated the self-attention scores for each input token.
Bam!
Now that we have the self-attention scores for the 3 tokens, we add the residual connections. And that just means that we add the values we had right after position encoding. And this last matrix contains the output from the encoder.
Double bam!
Now that we have finished doing the matrix math in the encoder, we can start doing the matrix math associated with the decoder. Note, to make this example more complete and interesting, we'll go through the math used during training. Specifically, we want to train the model so that the input tokens, SOS, Let's, and Go, are translated into the output tokens, Vamos followed by EOS, where EOS, which stands for end of sequence or end of sentence, is the token that tells the decoder to stop generating output. First, just like for the encoder, the decoder starts with a word embedding layer. However, in this example, because we want the output to be in Spanish, the decoder uses a different set of tokens. Specifically, the decoder uses these tokens: SOS, which is what we will use to initialize the decoder; EAR, the Spanish word for to go; Vamos, one way to say let's go in Spanish; E, the Spanish word for and EOS, which tells the decoder it's done generating output. Also, just like the encoder, our decoder uses 2 embedding values per token. Now, because we want the output from the decoder to be Vamos followed by EOS, then that means we want the first decoder unit to output Vamos. However, in order for the first decoder unit to output anything at all, we need to initialize it with something. So we'll use the SOS token to initialize the decoder. Now, like we said, ideally we want the first decoder to output Vamos. However, because we are training this transformer, regardless of what the output of the first decoder is, the second decoder will be initialized with the Vamos token. Initializing the decoders with known output values during training is called teacher forcing, and it makes training go faster. Anyway, once we initialize the second decoder with the Vamos token, we want it to output the EOS token, which tells the decoder that it is done generating output. Thus, our decoder has 2 input tokens, SOS and Vamos. And that means we multiply the weights in the word embedding matrix by a matrix with 5 columns, 1 for each token in the decoder's vocabulary, and 2 rows, one for each token. And doing the math extracts the word embedding values for the SOS token and Vamos. Now let's move the word embeddings for SOS and Vamos over to the left and add the position encoding just like before. Bam. Now that we have the encoded tokens, we can calculate the self-attention scores. During training, calculating the self-attention scores in the decoder starts out exactly like it does in the encoder. Using weights that are specific to the decoder, we calculate the queries, keys, and values. Then, using the Q, K, and V matrices, we calculate the unscaled dot product similarities between the queries and the keys for each combination of tokens. Then we scale the dot product similarities. Now, before we move on, I want to emphasize one specific detail. When we multiply the query for SOS by the key for Vamos, we get negative 0.12 as the unscaled similarity, and ultimately negative 0.08 as the scaled similarity between the query for SOS and the key for Vamos. This detail, that we calculated the scaled similarity between the query for SOS and the key for Vamos, will be very important in just a bit. So let's label it so it is easy to keep track of. Okay, going back to the scaled dot product similarities, now we do something we didn't do in the encoder. This has to do with the fact that during training, the input, let's go, should translate to Vamos. And we know that Vamos should come after the SOS token. And rather than doing all the math for SOS first, and then, sequentially, doing the math for Vamos, our knowledge that Vamos follows SOS lets us do it at the same time. So we can calculate the word embeddings for both tokens at the same time. And then we can add the position encoding values to each token at the same time. And we can also calculate the Q, V, and K matrices at the same time. Doing all this math at the same time, rather than sequentially, one token at a time, means we can train relatively quickly on hardware that allows for parallel computation. However, after training, when we want the transformer to translate something, all we know is that we start with the SOS token. And that means when we calculate the self-attention scores for the SOS token, it only knows about itself and nothing that comes after it. As a result, during training, even though we calculated all of the scaled dot product similarities for both tokens, we don't want to use the similarity between the SOS token and Vamos when calculating the self-attention score for the SOS token. So, during training, we only use the similarity between SOS and itself at the start of decoding. And then the decoder does the rest of the math not having any idea of what might come next, until it gets to the output. In contrast, because Vamos is the second token, it will incorporate what came before it when calculating the self-attention scores. And that means using both similarities that we calculated when we determined the self-attention scores for Vamos. In other words, we don't want tokens to cheat and peek at what comes next when calculating self-attention. But it is okay for a token to look at what came before it. The way that transformers keep track of what values should and shouldn't be used to calculate self-attention for each token is to take the scaled similarity matrix and add a mask to it. The mask matrix adds zeros to the values we want to include in the attention calculations, and negative infinity to any value that we need to ignore. What that means is that when we apply the softmax function to each row, the first token, SOS, has 100% similarity to itself and 0% similarity to anything that came after it. And thus, when we finally multiply the percentages by the value matrix, the self-attention scores for the SOS token do not include anything that came after it. Now that we have the masked self-attention scores for SOS and Vamos, we need to add the residual connections. So we take the self-attention scores and add the original word and position encodings to each token. Now we calculate encoder-decoder attention. The good news is that encoder-decoder attention is the same as calculating standard self-attention, except that the V and K matrices are created with the encoder's output matrix, and the Q matrix is created with the values from the decoder. So, we start with the decoder values we just calculated and multiply them by an encoder-decoder attention specific matrix of query weights to get the matrix Q. Then we take the output values from the encoder and multiply them by encoder-decoder attention-specific weight matrices to create K and V. And now we have Q calculated from the decoder values and K and V calculated from the encoder values. Then we just calculate the attention scores just like we did when we first calculated attention in the encoder. And now we have the encoder-decoder attention scores. Bam. The next step is to add the next set of residual connections. Then we run those values through a fully connected layer. In this example, the fully connected layer looks like this. It has 2 inputs for the 2 values we have calculated for each token, and 5 outputs, 1 for each token in the output vocabulary. As we saw with word embedding, the multiplication and summations that take place in this fully connected layer can be done for both tokens at the same time using matrix multiplication. And doing that math gives us this new matrix. We then add the bias terms to each column in the new matrix, and that gives us the outputs from the fully connected layer. Now we run the output from the fully connected layer through a softmax function, and we end up with a matrix that has the outputs from both copies of the decoder. The first row contains the outputs from the first decoder, and because the output for vamos is 1 and everything else is 0, vamos is the first token generated by the transformer. The second row contains the outputs from the second decoder, and the EOS token has the highest value, so it is the second token generated by the transformer, indicating that it is done with its work. Triple bam! Now it's time for some shameless self-promotion. If you want to review statistics and machine learning offline, check out the StatQuest PDF study guides and my book, The StatQuest Illustrated Guide to Machine Learning, at statquest.org. There's something for everyone. Hooray! We've made it to the end of another exciting StatQuest. If you like this StatQuest and want to see more, please subscribe. And if you want to support StatQuest, consider contributing to my Patreon campaign, becoming a channel member, buying 1 or 2 of my original songs or a t-shirt or a hoodie, or just donate. The links are in the description below. All right, until next time, Quest on!